last this session is going to be about robotics, computer vision, semantic acquisition, and Jana Koseka from University Symposium.
Thank you. Apologize for some of the technical difficulties outside. So today I'm going to talk about some problems related to semantic understanding of the streams of sensory data, which come from the sensors which are mounted on the robotic platforms, and this is a work joined with my students and postdocs over the past 3 years. So what is the problem of semantic labeling? So the problem of semantic labeling is the problem of simultaneous segmentation and categorization of partitions of sensory data into different semantic categories. And this is a very well studied problem in computer vision, and I would like to spend a little bit of time how tackling this problem in the robotics setting is different and what are both the challenges and opportunities. So in computer vision, one of the main motivations of trying to solve this problem is to try to associate some meaning with images. The semantic information typically provides this link to language. If you have language, then you can auto-annotate images, provide them with tags, and then these become sort of searchable by your internet engines, and they become sort of more of an equivalent of text. And so in computer vision, this is a very active area. There are a lot of approaches, and here would be one example of the state-of-the-art of a technique which does the semantic parsing. So you have an example of a street scene, and an output of the semantic labeling algorithm would be color coding individual pixels or regions into the semantic category. So the algorithm can predict the road, cars, wheels, buildings, windows, and so forth. And so in computer vision, these techniques typically consider single-view setting, and the types of data sets they work with are very unrestricted. So they're considered the whole internet collections where they, of course, first for performance evaluation, they gather some ground from data, but then proceed in this unrestricted setting, usually use quite expensive pre-processing technique and the learning and inference. And this is just to give you some feeling what are different types of semantic labels you can have. So you can associate the label with the entire image and calling it a street scene, or you can say, oh, there is a park, library, and maybe an intersection, or you can reason about objects which can appear at different locations and different scales, or you can actually go after the exact pixel level labeling. So this is just to highlight that this is a really difficult problem and a lot of variations of businesses. So just to give you a feeling of the variability of the type of data sets or images this problem is being tackled on, is there's a really extremely broad variety, and to some extent the current state-of-the-art techniques, you can argue that if you look at some average accuracy, one can sort of note a substantial progress. So it's about 80% of the pixels get correctly labeled by the algorithm. But the question is, how does it really help robotic applications? So can we really take these techniques and mount them on our robots, and 80% of all the sensory streams are really correctly interpreted, labeled, and recognized? And the answer is no, because these data sets have very strong biases, which are very different from the type of data we typically encounter in robotics. So, but nevertheless, I think there are a lot of opportunities to rethink this problem in a robotic setting, and with the hope that if we can provide some of this semantic understanding of the environment, we'll be able to facilitate more sophisticated tasks. The semantic information could provide this link to language and human-robot interaction. It will provide this sort of mechanism for symbol grounding problem, which can then is tightly coupled with sort of more traditional AI planning techniques. So I feel it's sort of a very fruitful area to pursue. And the type of application domains which we are thinking about in our settings are more sort of typical service applications, either in home or healthcare, where some basic navigation and fetch delivery tasks needs to be done, or in outdoor settings, these may be autonomous driving applications where you need to kind of analyze the scenes, understand where the bicyclists, pedestrians, what has changed, and so forth. So in the robotic setting, the main differences are that we typically have multiple sensing modalities, which is both provide an additional overhead, but also advantage that we can sort of measure different types of statistics of these environments. We have an additional advantage that we often, for particular tasks, often need very small number of semantic categories, right? So we don't have to really strive at the beginning for this huge scalability needed to recognize hundreds and hundreds of categories at the same time, but we can make these techniques more task dependent. And we need to also reason about the dynamic instances and dynamic scenes. And another advantage in the robotic setting that at the places where the performance of the computer vision techniques fails or reaches its limits, we can afford to deploy some active categorization techniques where we'll have capability of moving our sensors and getting a better viewpoint in order to resolve some of the ambiguities. So this is just sort of couple instantiations of these ideas, how the types of semantic information could be task dependent. So for example, when we need to do a navigation, it's important to know where the free space is, so we may need to detect the roads. And if we are interested in doing localization, it's good to know which structures undergo changes versus not. So for example, if I want to consider trees as landmarks, it's going to be quite unlikely they will be reliable if I want to localize the robot at the same location at a different season because they undergo large appearance variation. But on the other hand, building and sort of man-made structures serve as more natural landmarks. And then, of course, the sort of the remaining, the other dynamic objects, which can be then sort of categorized. So this sort of suggests that this task dependency suggests some natural sort of hierarchical categorization of these semantic labels. And one type of categorization that we propose is to first try to develop effective techniques to efficiently categorize the background categories, which vary in terms of depending on indoors-outdoors environment, and then have one generic category which are called objects, and then depending on the task, we can then refine the object category by deciding whether there are people or dynamic objects, car, bicyclists, and so forth. And so this, so what I'm going to discuss is I'll give you a brief overview of some of the techniques we developed for outdoors environments, where we have developed very effective techniques for these labeling into the ground, building, vegetation, skies, and objects, and then in indoors environments for ground, structure, furniture, and props, and then some follow-up approach, where we can then refine the props or object category to another 40 different categories of different types of furniture, lamps, chairs, and so forth, and sort of get some performance, which I think is very interesting for robotics applications. So another motivation for this hierarchy is that in a robotic setting, the need for this semantic information typically sort of happens at different time scales. So certain semantic information needs to be delivered very quickly. For example, I need to know where the free space is when I'm trying to avoid obstacles, but when I'm searching for some object, I can sort of deploy more sophisticated strategies which take longer computation and time, requiring completely more sophisticated features. So the sort of the semantic hierarchy also is related to different time scales of these different control sensor loops which operate in the system. So we are going to formulate the problem of semantic segmentation in the conditional random film framework, and I'm not going to go to technical details, but I'm just going to give you sort of a brief overview of the setting. So the conditional random fields formulate the semantic labeling problem as an inference problem on a graph. So in this case, the graph is induced by this small region. So we'll partition the images into small regions, which are called superpixels, and these will correspond to the nodes of the graph. And we'll have a learning procedure where we can learn how to predict different labels of individual superpixels and also how likely certain superpixels co-occur. So we can learn also the spatial relationships between these regions. And for the general graph structures, the learning and inference techniques are very expensive, and there are no, one can typically use only approximate techniques, which are often prone to converge to local minima. So what we do in a robotic setting is that due to the fact that we have also available 3D information associated with our sensory stream, which comes either through our 3D reconstruction pipeline, or in case of RGBD sensors, we have some 3D information available with these image regions. We approximate this graph using the minimum weight spanning tree algorithm, where the weights of the original graph are distances, mean distances in the 3D. So we basically break this graph into a tree where some of the edges are removed from the regions which are separated far away in the space, in the 3D space. And so this approximation puts us in the position that we can use these very efficient, exact algorithms for techniques which can train these conditional random fields and then do the inference. So this is just sort of one technical slide of how we proceed. So for each of these regions, we compute some features and make some predictions, and then the CRF learning algorithms learns the right weighting between all the features and all the spatial relationships in order to maximize the likelihood of the observation in some ground truth data. So this is just to give you a feeling what kind of predictions these techniques can generate. So here are some images of indoors RGBD scenes, and this is the ground truth labeling. So this is just for the evaluation purposes. So we have categories which are ground, blue is the furniture, yellow is the structure, and red is the objects. And this is what our algorithm can predict. So ground is usually very reliable. Structure and furniture can be sometimes confused because this depends where in the images, and itself the labels themselves are a little bit ambiguous, and then it sort of generates some probabilities. What are the likely locations of the objects? And this is sort of another example of another data set. And so once we have these regions which are more likely to contain objects, then we can also run our object prediction modules and generate actual hypotheses where the objects which might be manipulated are by having some prior knowledge of both sides of the object. And here are some of the hypotheses generated where the objects are. These hypotheses are generated in the absence of knowing what the object category is. So these are basically, object here is defined as a region in space which is surrounded by some opposing boundaries and have a particular size. So, and that would be kind of a hypothesis that this is already worthwhile exploring and maybe manipulating without necessarily knowing that this is a cup or a ball or something. And so similar types of techniques can be also applied to another setting, and I'm not going to go into details. And the semantic categories are of course different. So one thing which we are very excited and which I find sort of very appealing is that by choosing this hierarchy and going for recovery of a small number of semantic concepts, we can do it very efficiently. So these techniques, the entire feature computation and inference can run about 0.7 seconds per frame. So it's not quite real time, but sort of it can basically run in close to real time without any extra effort in implementation. And there was some follow-up work on implementing some of these modules on GPUs and more code in the C++, and then it can run about 5 frames per second. So another thing which is important, and here this is just to emphasize a little bit the strength of these conditional random field techniques, is that we often need to handle multiple sensing modalities, and the range sensing modality often has a lot of holes and gaps because in context of the RGB sensing, the places with high specularities or transparent surfaces, you typically do not have any returns. So those are the places where you do not have any 3D information, yet you would still like to infer something about these regions. And so in those cases, we can sort of set up these independent graph structures where, depending on whether you have both spatial and video information or sort of image information, or whether you have only one modality, we can infer these, predict these semantic labels everywhere, and the conditional random field sort of nicely propagates the evidence to the regions where the sensory information is not really present. So we have also extended these techniques into a recursive setting because I mentioned that we are interested in processing video sequences. And here the important idea is to kind of maintain some kind of temporal consistency of these labels. And that basically requires of propagating these graph structures over time and making some links and predictions. And we are linking these graph structures with the capabilities of actually computing the 3D pose between the consecutive views and then essentially solving some soft correspondence between the settings. So I'm not going to go through sort of technical details. Okay. So here I talked about this idea that we want to have a very fast and effective method for computing this coarse hierarchy. But now, depending on the task, we may need to refine it. So suppose that at some level, I may need, in order to navigate to a certain room, all I may care about is where the floor is and where the furniture is. But if I need to open a door into a refrigerator, I need to be able to have some finer categorization of the furniture category to be able to distinguish refrigerator from the cupboard. And then I have to go even further because I may need to know where the cabinet and the door is and where the door handle is. So there are different levels of hierarchies. This is the so-called spatial hierarchy because things occur at different spatial scales. And you should really design the algorithms such that they can handle it properly. And majority of the techniques consider a single flat hierarchy where all these techniques are discovered, all these labels are discovered independently. Another type of hierarchy is a type of hierarchy, right? So if you, for example, want your robot to fetch a drink, soda drink from the refrigerator, you may not care that much whether it will be Coke versus Sprite as long as one of them can be found. So if you do not have enough confidence in finding the Coke once you open the refrigerator, then you can move one level up to the hierarchy and get the soda drink or some kind of container. And so we were thinking, so there are some thoughts on how to tackle these hierarchies. And so and we are sort of currently very much interested in this problem. And so we have made some first tries in order to tackle it by refining the furniture and objects hierarchy in our setting. And so the way how we have decided to do it is to take the initial representations which we used in the previous setting and compute some more informative features, because now we need more discrimination capabilities in order to disambiguate between different types of furniture. And then instead of, again, trying to solve this complicated multi-class inference problem, we approached it by designing a lot of very simple binary segmentation tasks, which we can then apply in a sequential setting. And so this then sort of affords some modularity, which enables us to invoke depending on the task constraints. And another appeal of this sort of inexpensive sort of binary recognition and segmentation tasks that we can really train them very efficiently, and we can exploit various covariance constraints between different object categories. All right, so here are some examples now how we can then sort of detect sofas and chairs and beds and tables in this particular setting. And these examples are, here are some of the unsuccessful examples, but the average accuracy is in the order of 60 to 70%. So here I sort of want to advertise and encourage you to think about the following problem. And so in computer vision, and so far in the majority of the evaluation platforms, the algorithms finish here, right? So they generate a prediction of a particular object category. And you can see there are a lot of uncertainties because it can be a sunscreen or espresso maker, or there are a lot of possibilities of what kind of objects they can be. And if there is a threshold on the algorithm, and if the threshold said, I'm going to accept hypothesis only when it's greater than 0.5%, the algorithm will declare this as a failure. But you can see that just changing the viewpoint and changing the scale, you can dramatically disambiguate the type of perception you have. And this is something which the computer vision evaluation data sets really don't have at their disposal. And so I think it would be sort of wonderful if some more joint efforts could be carried out in this setting. And we are sort of making some effort to collect the data set where multiple groups can do these types of experiments. Because difficulty here is that there is this motion component that, so how to sort of simulate it or factor it in such that and everybody can kind of do it in some repeatable way without actually having to have the robot to move around. So I think I'm just going to conclude. So here were sort of a few snapshots for how to apply these techniques and what are the challenges and opportunities in robotics. So one part which I think we feel very excited is that I think when these things are thought through carefully and designed, they actually can be quite computationally efficient and already useful in robotic settings. So where we have all sorts of constraints in needing to run things in real time, needing to run things in a controlled of a system. And we feel that having that hierarchical representation is quite critical. So we want to have a lot of simple features and statistics to compute the core classes and then refine them depending on the task. We also believe that we should think of techniques which exploit the environment constraints, because in a robotic setting, you are not, the imagery and data is very different. You have a lot of constraints which you can exploit. And once you exploit these constraints, you need to then learn how to adapt them to slightly different environments. So you don't have to relearn everything from scratch. And I think also sort of thinking about this active object search and object categorization strategies can just dramatically push that envelope of what is currently the state-of-the-art performance in the existing techniques. Thank you.
Time for one question.
Thanks for the talk. So in your introduction, you mentioned semantic labeling is closely related to robot vision. Do you have any specific idea of how to combine these two efforts to improve each other?
So we have recently made such effort. So if you want to have these robots operating over extended periods of time and make them localized in the environments which undergo dynamic changes, the semantic information is very helpful. Because if you have some information about objects which undergo changes in appearance over, say, seasons or periods of time, then you can kind of discount them properly depending on the choice of your localization technique. Similarly, if you know that something is a dynamic object which is movable, and your localization algorithm will pick it as a landmark when it's learning the map, and if it cannot find it when it's revisiting the place, unless you have that information, you could easily declare failure. But if you know that, hey, this was just a car, it was not a landmark, then you can more gracefully recover. So this discussion should be a little bit more specific because it's very closely tied to what is your localization strategy. So this was a localization strategy where the semantic information is combined with any kind of generic appearance features you may use for localization. But even sort of the basic feature matching techniques, which are used for establishing correspondences, can benefit greatly by having some information about the semantic categories. So you know that locally, a little feature which comes from the sky may look exactly the same as the one which comes from the building, but if you know that they come from different semantic categories, you would never be tracked, you can never match them together. So it's both at this very low level of establishing the correspondences, but also at the level of dynamic changes in the environment over extended period of time.
Thank you.